This is the lesson for 3.6 Complex Zeros in the Fundamental Theorem of Algebra for pre-calculus class. I want to review what we've been learning the last few days, it's actually a review of a review, but that is that all the numbers, all real numbers that we talk about, numbers 1, 2, 3, the integers, the fractions, everything, they're all really part of the complex number system. They just don't have any imaginary part, but they're still all part of the complex number system. And so we could think of it as it's a plus bi, it's just that the b is 0, so you don't see this term at all, you just see the a, which is the real part of a complex number. And all imaginary numbers are also part of the complex number system. They can be just the bi, or they can be both the a and the bi. So when the a is 0, you have just the imaginary part, bi. Okay? All numbers that we know, everything you've ever seen, from all your years of schooling and everything that you've ever done, and that we talk about in this class are part of the complex number system. The fundamental theorem of algebra, we've talked about this a little bit before, and that is that as long as we're in the complex number system, we're not just talking about real numbers only, but we're talking about complex numbers that can be a combination of real and imaginary. When we're in that system and we're talking about nth degree polynomials, then they're going to have exactly n roots. That's if we're counting multiplicities. When the roots are real, we can see them when we graph the polynomial, and we see them as x-intercepts. When there's even multiplicities, like if there's 2 zeros at 5, then it will bounce in the graph. It will bounce at 5. It could either bounce up, where we could have something that looks like it's bouncing up like this on the x-axis, or it could be something that is bouncing down like this. Either way, those are called bouncing if this is the x-axis. All right. So we have bouncing if there's even number of multiplicities. It could be 2 or 4 or 6 or 8, things like that. If there's odd multiplicities, so there's 1 0 at 5, or there's 3 zeros at 5, or 7 zeros at 5, then it's going to pass through. So in that case, we've got our x-axis, and we're going to have something that goes through like this, or it could go like this, kind of wiggle through it. Okay, it could also coming down. Those are multiplicities that are odd number of multiplicities. When our roots, our zeros, have imaginary parts, when we graph, we can't see them. They're not on the x-axis. They're not visible to us in the same way that real roots are visible as intercepts of the x-axis. So let's look at this parabola, this quadratic, the second degree polynomial. You can see here it is right here, and the x-axis is all the way down here. It doesn't have any x-intercepts, but we know since it is a second degree polynomial, it must have 2 roots. Well, let's solve it to find out. We set it equal to 0, because that's what roots are, is when the equation equals 0. Since it doesn't have any, we set it equal to 0, and we're going to solve this. So we're going to subtract 4 from both sides. Then we're going to take the square root of both sides. Oh, we're taking the square root of a negative number. That's going to give us an imaginary. The square root of negative 4 is 2i, so we get plus or minus 2i. And we still have x minus 1, so we're going to add 1 to both sides. And then I'm going to write that as the 2 numbers. I'm not going to keep using plus and minus. I need to write them separately, because I need to show that this is one of the roots, 1 plus 2i, and this is one of the roots, 1 minus 2i. Or another way to say it, they're the 2 zeros. And even though they don't cross the x-axis, they are what makes this equation equal to 0. Since those are the roots, we can write our polynomial that we had here, and in this form, this was in the standard form or vertex form, we can now write it in its factored form. And the factored form is always going to be x minus each of the zeros. So I have x minus 1 plus 2i, and I have x minus 1 minus 2i. And notice that I have those zeros in parentheses themselves, because we're going to have to distribute this subtraction symbol. Okay? So what does it mean to factor completely? Well, there's steps that we follow, and the first step is to list all possible rational roots. And that's where we looked at the factors of the constant divided by the factors of the leading coefficient. We then take that from that list of possible roots, test them to actually find at least one or two zeros in that list. Then we use synthetic division with one or two of those zeros until we can get a result that is a second degree polynomial, meaning there will be three coefficients in our synthetic division. Once we get down to a quadratic, we can either use the quadratic formula, which is most common, or if you can factor it, you could factor it to find the remaining zeros. But typically what we're doing right now is practicing that we're not going to be able to factor. We'll have to use the quadratic formula to find the remaining zeros. They could be real or they could be imaginary. Once we have those, we list the zeros out. I call them like C sub 1, C sub 2, C sub 3, C sub 4, however many there are. Remember, if it's an nth degree polynomial, there will be n of these zeros. So if it was a fifth degree polynomial, there should be 5 zeros listed. You're going to write the factorization as a product of all the factors, writing it as x minus each one of those c's. Remember to use parentheses for complex. Now, if they had said, put your final answer in simplified form, there wouldn't be parentheses, but this is the goal of factoring, trying to factor our polynomials. Okay? So here's an example. We've got it in general form, and we want to write this polynomial in its factored form. So step number 1 is to list all possible zeros. I see that it's third degree, so I know there will be 3 zeros. I go into this knowing that. List my possible rational zeros. I take all of the factors of 20, which is going to be plus or minus 1, plus or minus 2, plus or minus 4, plus or minus 5, plus or minus 10, and plus or minus 20. Each of those divided by the factors of the leading coefficient. But in this case, since my leading coefficient is 1, it's just the factors of 20. So I list them out. I then start testing those. I start plugging them in. I like to always start with the easiest ones first, 1 and negative 1, and I don't get 0. The whole point is you plug in the 1. If it equaled 0, it would be a 0, but plugging in a 1, I don't get 0. I don't even need to know exactly what it is. I just start the process and realize this is not going to get me 0. And same thing if I plug in a negative 1, it's not going to get me 0. When I plug in a 2, I find that, I got 8 minus 16 plus 28 minus 20. That equals 0, so that is one of my zeros. And since this is third degree, I only need to find 1, because when I do my synthetic division, I'm going to go from a third degree to a second degree. There it is. There's my second degree, my quadratic. And this is the ax squared plus bx plus c. I'm not even going to write this as a quadratic. I just recognize that that is a quadratic with my a, b, and c. And I'm going to go straight to using the quadratic formula, where I've got x is equal to negative b plus or minus the square root of b squared minus 4ac all over 2. And I'm going to simplify, and I get the negative 36 under the square root, so that's going to be plus or minus 6i. Excuse me. Oh, hold on a minute. That's incorrect. No, it's fine. This is plus or minus 6i, but I'm dividing everything by 2. So 2 divided by 2 is 1, and 6i divided by 2 is 3i. So this is the simplification. I forgot that I went straight to the final answer there. I've got my 2 zeros, so I'm going to list my zeros now. And here I've listed my zeros. 2, 1 plus 3i, 1 minus 3i. Please make sure you're listing them out as separate numbers. Don't write it as plus or minus. And the reason for that is because from this list, we're going to be able to write the factorization. And we're just going to write x minus each one of those zeros. But here I've got my complex numbers with their parentheses. Now I'm going to do the distribution of that subtraction. And I have my final answer of my the factorization of this polynomial, completely factored. Okay, now all complex zeros, the ones with imaginary parts, have a conjugate that must also be a zero. So you can't just have one complex zero. They always travel in pairs, and they are conjugate pairs. So what this is saying is, if 3 plus 2i is a zero, if you find out you're given this, or you figure it out through factoring or something, you can get 3 plus 2i is a zero, then it must be that 3 minus 2i is also a zero of that same polynomial. If 8 minus I is a zero, then 8 plus I must also be a zero. They have to travel in pairs. If negative 5i is a zero of L of x, a polynomial, then positive 5i must be a zero of that same polynomial. How do we see that? In the work you're going to do, we're going to see where they're going to give you only maybe one of them, and you're going to have to figure out that you have another. So here's a concept that zeros are not unique, meaning different polynomials, they'll have different graphs and everything. They different polynomials, and they can have the same zeros, the same x-intercepts, or the same complex zeros as well. Let's look at a problem the way it would be given in the book. They're telling you that they're thinking of a fourth degree polynomial with the following zeros: 3, negative 1/2, and 2i. And this is where you go, wait a minute, it says fourth degree, but I only see 3 zeros here. And that's when you turn your attention to, they only gave you 2i. And you think, wait a minute, it's got to have 4 zeros, and since 2i is in the list, negative 2i must also be one of the zeros, and they just didn't tell you. So now you know the 4 zeros, and I write x minus each one of those zeros. So I had x minus 3, I had x minus negative 1/2, meaning x plus 1/2, x minus 2i, and x minus negative 2i. To multiply all that together to write this polynomial in simplified form, which is what you'd have to do, I'm going to multiply these two binomials together, and I'm going to multiply these, and these are the conjugate pair, so you're always going to get the first one squared minus the last one squared. Well, 2i squared is negative 4, and since it's going to be x minus negative 4, x squared minus negative 4, we write x squared plus 4. Now we need to multiply this trinomial times this binomial, and in the end, we get this polynomial. But I want you to see over here, which I just put up here as well, this right here, 2x plus 1, this would have a zero of negative 1/2, just like x plus 1/2 did. Both of these factors have a zero at negative 1/2. But when you multiply this group of factors together, you get a different polynomial. And if you look at it, every single term has been multiplied by 2 from this one. They don't graph the same polynomial, the same fourth degree polynomial. They will look different. They have the same x-intercepts. What I want you to do now is I want you to do these 4 problems where you're going to completely factor. That's all the way down to just binomials that you're multiplying, x minus each of the zeros. So you have to go all the way. And the second problem is to write a polynomial given these 2 different sets, so you can write 2 different polynomials, p of x and q of x, with the given situation. When you're doing the factorization up here, a through d, really make sure you're looking for patterns. These aren't all, oh, I have to do synthetic division, or I have to do the rational root test and everything. Look at them carefully, because a couple of these have very specific patterns to them, and you can factor them by knowing some of your pattern factorization, okay? And we will go over these first thing on Monday.